right, bottom half of 140, we want to finish off section 3.2 talking about the derivative as a function. And on the bottom of 140, they tell me that there are a lot of different notations that we're going to use for the derivative, or the symbolism to tell me to take the derivative or to differentiate. There are a lot of different ways that we say that as well. So when we say that we want you to find the derivative of something, they might say differentiate, because that's the process of taking the derivative. Or they might ask you to use a differentiation operator. Those are bold print terms on the bottom of 140. But in essence, these are the different notations that you're going to see them use. Now, the reason there are so many of them is there are actually two different gentlemen who came up with the concept of calculus at the same time. And that was Leibniz and Newton. So Gottfried Leibniz and Sir Isaac Newton both discovered the ideas of calculus at the same time. However, Leibniz, bless his heart, was actually accused of plagiarism by the Mathematics Society of that time. They thought he had stolen somebody else's ideas and presented them as his own. So how sad is that? You come up with something as amazing as differential calculus and then you don't get credit for it. So they did finally realize that both Leibniz and Newton had come up with the ideas simultaneously, independently on their own, that they were both geniuses and deserved credit. And so that's one of the reasons that we keep all of these different notations, because some of them are from Leibniz and some of them are from Newton, and we keep both of them to honor both gentlemen. So here's the notation that they've already showed us, the derivative. So f prime x. Since f of x is the same thing as y, sometimes they might say y prime as a way to write the derivative. Or they might say dy dx. Now you've seen that already, like on the calculator. When we were using derivative on the calculator, that was the notation that your calculator uses. They might also say df over dx, like the function df. Or they might write it this way, like the derivative of the function, or the derivative of the function, or the derivative of the function. So several different ways that we might see that. We've also seen them ask me to find the derivative at a particular value. Like if they wanted me to find the derivative at 5, with that notation that we were using with the, f prime, we would say f prime of 5, and that just meant put 5 in the place of x in that notation. How you would write that with some of these other operator notations is something like this. I would say find the derivative, and I could draw a line there and say at the value where x is equal to 5. So that's the notation that you'll see them using. Okay? So over on page 141, we want to focus today on what makes a function differentiable. And differentiable, if it's differentiable, that just means you can take the derivative of it. So there on 141 in the red definition box number 3, it says a function f is differentiable at a if the derivative of f of a exists. So that's simple enough, right? It's differentiable if the derivative exists. So what's going to make my derivative not exist? Well, it just goes back to the idea of domain again, right? They could be saying here that a function is differentiable at a for all values within the domain of the derivative. So they could say if you take the derivative and just think about what the domain of that derivative is, it's going to be differentiable everywhere it exists. So typically when we're talking about domain, we say domain is all real numbers unless one of two things happens. You get a 0 in the denominator, or you get a negative under an even indexed radical, like a square root or a fourth root or something like that. So the easiest way to tell where something is differentiable is to actually take its derivative and look at where that derivative's domain is. Where does it exist? So for this first one right here, we've got if the derivative is equal to the square root of x plus 2, then where is that function differentiable? Well, it's going to be differentiable everywhere the derivative exists. So where does that derivative not exist? It doesn't exist anywhere I get a 0 in the denominator or a negative under an even indexed radical, right? So I don't have a denominator, but I do have an even indexed radical. So I would want to say, okay, whatever's underneath that square root can't be negative because that would give me imaginary. It needs to be greater than or equal to 0. And then we could just solve that inequality. And we would get the interval on which that derivative exists. So that would tell us where it was differentiable. Now, they also mentioned there on page 141 that if it's differentiable on an open interval, AB or A infinity or negative infinity A or something like that, that will be true if it's differentiable at every number in that interval. So it can also, it doesn't have to be differentiable everywhere. It can be differentiable just on a particular interval as we saw here. All right, look at another one. For the next one, they tell me that my derivative is equal to 1 over x plus 2. So where would that be differentiable? Yeah, everywhere except for where the denominator is going to equal 0. So we can just say if my denominator equals 0, if x plus 2 is equal to 0, that's at negative 2. I'm going to have to exclude that. There's not going to be a problem anywhere else. So everywhere except for that negative 2. All right, look at example 6. Page 141, example 6. It says, where is the function f of x is equal to the absolute value of x differentiable? All right, so we're going to break this down and we're going to analyze this a little more thoroughly than what we were just doing, because absolute value, as we know, is a piecewise defined function. So the first thing I'm going to do is I'm going to redefine this absolute value as a piecewise. So I'm going to say, okay, I'm going to get the absolute value of x to be x if x is greater than or equal to 0, or negative x if x is less than 0, because if what's inside your absolute value is greater than or equal to 0, you get what you started with. If it's less than 0, then you get the opposite of what you started with, right? So let's go through and let's analyze all three pieces of this. Let's think about, where is it less than 0, where is it greater than 0, and where is it equal to 0. We'll look at all three of those components and see what type of decisions that we can make, because that would be all real numbers from negative infinity to positive infinity if we looked at all three of those pieces. So first off, let's think about if x is less than 0. If x is less than 0, then the absolute value of x is going to be negative x. So if I go through and I'm trying to think about what this derivative is going to look like for values less than 0, definition of derivative is the limit as h approaches 0. We'll come back and talk about this notation in a few minutes. Limit as h approaches 0. And I'm going to look at this as the limit from the left, of course, because we're looking at 0 values less than 0. And so remember that our definition is f of x plus h minus f of x divided by h. So if we did f of x plus h, that means put x plus h in the place of x in your function. So that means that we would be putting x plus h in the place of x in that absolute value. So that would give us absolute value of f of x plus h. So there's, absolute value of x plus h. So there's f of x plus h minus f of x, which is just our regular function, divided by h, right? So if we work with that, because we're looking at values less than 0, we've said that the absolute value would be the opposite of what you started with. So when we do the absolute value of x plus h, we're going to get the opposite of what we started with, negative x plus h. And the absolute value of x, we're going to get the opposite of what we started with, negative x, all divided by h. So if I distribute, I'm going to have negative x minus h plus x. So x and negative x drop out and just leave me negative h over h. The h's drop out and just leave me negative 1. So now I have the limit of negative 1. The limit of a constant is that constant, so I would get negative 1. So yes, this is differentiable for all values less than 0. Any number that I put in for less than 0, every single one of those, I'm going to get a derivative of negative 1. So yeah, the derivative is going to exist, right? Let's think about values greater than 0. So if I go through and I say, okay, if I'm working with values greater than 0, I'm going to start the same way. The limit as h approaches 0 of absolute value of x plus h minus absolute value of x over h, because again, we've done f of x plus h minus f of x divided by h. When we do the absolute value of x plus h, though, when we're thinking of values greater than 0 or approaching 0 from the right-hand side, then when you take the absolute value, you get exactly what you started with. So we're going to, absolute value of x plus h would be x plus h, and the absolute value of x would just be x. So x plus h minus x is going to leave me just h in my numerator. H over h simplifies down to 1, and the limit of any constant is that constant. So this is also differentiable for all values greater than 0. If I went through and I evaluated the derivative at any value greater than 0 every single time, I would just get a derivative of 1. So then let's look at 0 itself. So if I go through and I think about when x is equal to 0 and I take the derivative, then I'm going to put 0 in the place of x. So that would be f of x plus h, where we've put 0 in for x, minus f of x, where we've put 0 in for x, divided by h. So if I put 0 plus h in the place of x, that'd be the absolute value of 0 plus h. If I put 0 in the place of x, that'd be the absolute value of 0 all over h. So I'm going to get the absolute value of h in the top, and I'm going to get a plain h in the bottom. So when I come down here and I think about this as the limit as h approaches 0, I'm going to have to think about that limit from the left and from the right, because it's different with the absolute value. If I'm taking the limit as h approaches 0 from the right-hand side, then all of the values that I'm putting in for h up here are going to be greater than 0, so the absolute value of a positive number is just that same number. I would just get h, so h over h would give me 1. But if I'm looking at this as I approach 0 from the left-hand side, when I do absolute value, all of those values are going to be less than 0, so if you take the absolute value of a negative number, you get the opposite of what you started with, so negative h over h is going to give me negative 1. And we've learned that the limit from the left doesn't equal the limit from the right. That means the overall limit doesn't exist. So if the definition of derivative doesn't exist at 0, then that just means that the derivative does not exist at 0. Now, there are very few times that I have to supplement your textbook. We have a phenomenal textbook, but this is one of those times. Because the notation that I used back here, this little guy right here and this little guy right here, and you see it again written down here, what is that? Look, if you would, at page 146, homework problem number 40. In the middle of the homework problems, they give you a bold print term. They give you a definition of derivative from the left and derivative from the right as a bold print term in the middle of the homework. That's terrible. That's an important thing, and they just happen to mention it as an afterthought in the middle of the homework. Who looks for a bold print term in the homework problems? So in your notes packet, you will find a couple of pages from a different calculus textbook that give you just a better explanation of that idea of derivative from the left and derivative from the right. But if we think about the definition of derivative as being that limit, literally when you're doing a derivative from the left and a derivative from the right, it's the same idea as doing a limit from the left and a limit from the right. So let's go back to example number 6. If I wanted to find the derivative for the values less than 0, I could write that as the derivative from the left, and whether you're looking at homework problem number 40, bold print term on page 146, or whether you're looking at that handout that I gave you from the other textbook, they tell you that this is the notation that we're going to use for derivative from the left, and this is the notation that we're going to use for derivative from the right. So we just put that little subscript of a plus sign or a minus sign to show whether it's the derivative from the left or the derivative from the right. And you could also put a particular number in there if you want the derivative at a value. Though, like if we wanted to say the derivative from the right of 0 and the derivative from the left of 0, we could just put a 0 in there as well. So, if I looked at this as the derivative from the left, and I looked at this as the derivative from the right, and the derivative, again, by definition, is just a limit, I wouldn't necessarily need to do all of this work down here to figure out what's going on at 0. Because right here, I got the derivative from the left was -1 and the derivative from the right was +1. Just like a limit, if the derivative from the left doesn't equal the derivative from the right, then that derivative is not going to exist where those two pieces are coming together. So if I'm analyzing this as I approach 0 from the right and 0 from the left, and I get my derivatives to not equal each other, that means the derivative is not going to exist at 0. But I also had that reinforced down here when I actually tried to evaluate with the derivative formula. I actually tried to evaluate that limit from the left and from the right, and I found out that the limit did not exist at 0, and that meant that also it was not differentiable at 0. So that just is a more reinforcement for us of that definition that they're giving us. So if you want to know if something is differentiable at a particular value, you can look at the derivative from the left and the derivative from the right, and they need to equal each other. That particularly comes into play when I'm working with a piecewise defined function. Like, let's say that they give me a piece when x is less than 2 and a piece when x is greater than 2, and they want to know if it's differentiable at 2. Then I'm going to take the derivative of that function from the left, and I'm going to take the derivative of that function from the right and plug 2 in and make sure that I'm getting the same thing from the left and from the right. Okay, so again, a little bit of explanation of that in homework problem number 40, but a much better explanation on that handout that I gave you. So please be sure that you look at those couple of pages and make sure that you're concrete on that idea. Okay, so differentiability is going to be an extremely important topic for us. They're going to ask us to determine if something is differentiable pretty frequently. So you're telling me that every time they ask me to check for differentiability, I have to do this craziness that we just saw here? Not necessarily. Let's get practical. In the middle of page 142, they give me a theorem that says if your function is differentiable at A, the function is also continuous at A. But the converse of that is not true. There's a little Ghostbuster symbol over in the middle of 143. The converse of theorem 4 is false. That is, there are functions that are continuous but not differentiable. Look at this one we just talked about. Can I draw the absolute value function without picking up my pencil? Yes, that thing is continuous everywhere. But we just found out that it was not differentiable at 0. So if I prove that something is differentiable, that automatically means it is also continuous. So I won't have to go back and prove continuity if I've already proved differentiability. However, just because something is continuous does not mean it will also be differentiable. So that's what we've stated here in your notes. If a function is differentiable at A, then it is also continuous at A, but the converse of that is not true. Okay, so how am I supposed to tell then, practically, where something is differentiable and where it's not? We have that fun little rule for continuity, right? Anywhere you can draw it without picking up your pencil, it's continuous. So here's a practical way to test for differentiability. On the bottom of 143, they tell me that your function will be differentiable unless one of three things happens. Number one, you have a discontinuity. Anywhere that your function is discontinuous, it is immediately not differentiable there. No questions asked. So anywhere that it is discontinuous, it is not differentiable. I don't even have to say why it's discontinuous. Like for this guy right here, I don't have to say that it's discontinuous because the limit from the left doesn't equal the limit from the right, therefore the limit doesn't exist. I don't have to say that. For my justification for why it's not differentiable at whatever that value might be, all I have to say is discontinuity. If I want to be more specific and say why it's not continuous, that's fine, but I don't have to. The second thing that will cause something to not be differentiable, the book calls a corner or a kink. Go back to that one we had just a second ago. If I were looking at the absolute value graph, there's nowhere that that's not continuous. So how am I supposed to figure out that it's not differentiable there? Anywhere that your graph has a corner or a kink, it will not be differentiable. Why? Because think about the idea of the derivative as the slope of the tangent line, all right? If you think about it, anywhere your graph comes to a corner, if you were to draw a tangent line right there, that tangent line is going to have a positive slope, but that tangent line is going to have a negative slope, right? And that would always be true at a corner. So for that reason, anywhere you see a corner in your graph, the derivative from the left is not going to equal the derivative from the right. Now, for AP purposes, if you say I have a discontinuity right here at this value, not discontinuity, I'm sorry. If you say that my function is not differentiable at that value right there, and they say justify your answer, do not write there's a corner in my graph. That doesn't work for AP. It'll say that in the back of our textbook as the answer to the odd problems when it says give a reason for why it's not differentiable. We can't say that for AP. We have to say the derivative from the right does not equal the derivative from the left. I can say that just as fast as I can say there's a corner or a kink in my graph, okay? And that will always be the case. Anywhere your graph comes to a corner, it comes to a point, the derivative from the left won't equal the derivative from the right there. That's my justification. The third thing that will cause my function to not be differentiable is a vertical tangent line. What's the slope of a vertical line? Undefined, right? Doesn't exist, right? So if slope of a tangent line is derivative, and you just told me the slope of a vertical line does not exist, that's where your derivative would not exist, right? So that's another way that you can have something not differentiable. So anywhere that you can draw a vertical tangent line, it's not differentiable. Now let me stress one thing, because they give us this picture in the book where you kind of have the thing coming down to 2 points, and it almost looks like anywhere you have an asymptote, you're going to have a vertical tangent line. That's not true. If you have an asymptote, as your graph approaches that asymptote, it is continually changing, right? I know, only minutely, but it is continually changing. So if you drew a tangent line, it would not be perfectly vertical. It would have a slight slant to it. It would not be a vertical tangent line. So don't go through and anywhere you have an asymptote automatically say that it's not differentiable. If you have a vertical asymptote, your function doesn't even exist there, right? So, but you don't necessarily have a vertical tangent line anytime you have something running off to infinity or something like that. That is a continually changing value, okay? All right, so here is our homework for tonight on pages 145 to 146.